About a year ago, I uploaded a video which showed my progress on creating a model of GLaDOS from the Portal series as a ceiling lamp. The greater goal is to build a self-written home assistant based on it, and first tests of voice recognition and actions triggered by commands were demonstrated at the end of the video. The main question, that was also asked by quite a lot of people in the comments, is: how does it actually work? This video will go over the essential parts of the whole assembly and the program. Hello everyone, welcome to another technical video. This time I will go over everything regarding the assembly and programming of my model of GLaDOS, which was shown in a previous video. This will include all essential mechanical, electrical and software components. If you are interested in a specific topic, I marked them for you by using YouTube's chapters function. First I want to give a broad and general overview of what I will cover. In total, I will cover 6 main topics: the mechanical components, the electrical wiring, the general assembly, all used programs, what tests I did, and finally, what I have currently planned. This overview will be used again at the beginning of each chapter to help as a guide which topics will be covered next. Another thing, when you are seeing short texts like this one in the lower left corner, this is a reference for online sources. You can find the same text in the video description with the corresponding source. The total setup consists of 3 individual objects that are connected by one large cable. The first object is the model of GLaDOS itself. It is oriented in the middle and serves as an actuator that can be controlled by sending commands over the cable. The second object is the control unit on which all the essential program logic runs. Here, the voice recognition and sound output are handled, as well as sending commands to GLaDOS. The last object is a small connector box. This is currently not in use, but is implemented to serve as a hub for future devices that should be added to the system. This connector box contains terminals for power and data transmission, meaning that these devices will be able to exchange data with the control unit. These 3 objects combined are the current setup that I use for GLaDOS. Each object will be explained simultaneously during the next chapters. First up are the mechanical components used in the entire setup. When I started the general project, I found an Instructable online which covered the assembly process of a model of GLaDOS. The original creator, Dragonator on Instructables.com, explained in detail which components need to be assembled how, and used lots of images to help with the assembly process. I want to thank the original creator of the Instructable and the 3D model of GLaDOS for making his work publicly available, so that anyone like me can build one themselves. I linked the Instructable of the original creator in the video description, so definitely check it out. The whole body of GLaDOS consists of 26 individual 3D models, of which some need to be printed multiple times. In total, the body is built out of 39 printed parts plus electronics and other mechanical parts like screws. The body starts with a mounting ring that is bolted onto the ceiling using multiple screws. This acts as the anchor for the whole rest of the body. To this ring, a big cylinder is mounted. Everything else is connected to this part. It contains the servo and 2 gears for the first axis of GLaDOS, which allows her to rotate around the base. I used this compartment for the microcontroller and PWM driver board, but more on that later. The outer ring consists of 16 individual parts with 8 channels and 8 lids. These channels latch onto each other and are mounted onto the big cylinder using a screw. The small tubes between the channels and the cylinder function as a mounting point and cable channels at the same time. Note that the small cable channels might need to be drilled out in order to be able to feed cables through. These channels will later house LEDs, and I used them also to contain the required electronics for power. The channels are designed to be used as cooling ducts for the LEDs by mounting 2 40mm fans in the design slots. The servo in the cylinder is connected to a main pivot tube. Onto this, the next part of GLaDOS body is mounted. This part consists of multiple solids, the white back plate and the inner black body. The small holes on the sides allow cables to be routed more neatly. The next part of the body is mounted on the bottom of the servo and is called the main arm. This part can move up and down by a push rod which is connected to the previous servo. The main arm also contains another servo which will rotate the next part called rotation. It allows the final part, the head, to be rotated sideways and also contains another servo. The servo is connected to the head using another push rod and moves the head up and down. The head is one single piece which has a cutout on the eye to allow an LED to be mounted. This LED will be later referred to as the eye LED or just eye. All prints combined took about 140 hours to complete, using roughly 1.4 kg of PLA filament. The parts were printed in either black or white, depending on which color is more visible in the finished part. Some parts also required painting, as they contained multiple colors and small features, like the small red dots on some body parts. For this, some additional stamps were designed and printed to help with applying the small features. The parts were first primed and, after letting them dry, painted in the right color. This process took roughly 24 hours, mainly just to let the paint dry. While we were at it, we also printed and painted some other smaller things like a companion cube or a 1500 megawatt Aperture Science heavy-duty supercolliding super button, just for good measure. The control unit consists of a Raspberry Pi 7-inch touch display, a Smarty Pi display case, a mount for PCBs and 2 PCBs for logic level converter, and a step-up module. The PCB mount was designed and printed by myself. The connector box only consists of a case and a PCB with terminals to connect wires to it. After giving an overview over all mechanical components, I want to do the same for the electrical wiring. This is meant as an overview to give an idea on which components are connected to each other in which way. I will start again with the wiring of the body of GLaDOS. Inside the body, there are 2 different power rails, 12 volts and 5 volts. The 12 volts are for the LEDs and fans in the ring, and the 5 volts are for the microcontroller, PWM board and the servo motors. All power supplies are connected to AC power in the ceiling, with an exception for the 12 volt power supply for the LEDs. Its connection is interrupted by a relay, which can be controlled with a microcontroller. Connecting it after the relay has the advantage of reduced power consumption when the LEDs are turned off, but comes with a noticeable delay between enabling the relay and the LEDs actually lighting up. The 4 servo motors inside the body are all connected to pins 12 to 15 on the PWM board, with the main rotary motor on pin 12, the pivot motor on pin 14, the sideways rotation motor on pin 13, and the head motor on pin 15. The order of the pins does not really matter in this case, they just need to be used correctly in the program later. The PWM board is connected to the 5 volt power supply to provide power for the servo motors and to the I2C lines of the microcontroller. For the microcontroller, an Arduino Nano was chosen. Its I2C lines are on pin 27 and 28, or A4 and A5. The Nano receives its power from the 5 volt power supply via the pins V-in and ground. The remaining parts of the wiring are shown in this part of the diagram. The relay is controlled via an NPN transistor to provide enough current for the relay. The transistor is controlled via the pin D8 of the Nano and conducts 5 volt power if enabled. The orange LED in the eye is directly controlled with pin D9 of the Nano. Note that the 220 ohm resistor is in series to the LED. Lastly, pins D10 and D11 of the Nano are for data transmission between the Nano and the Pi. These 2 lines connect to the outside of GLaDOS body. In addition, a mini USB cable was cut in half and plugged into the Nano. The open end was put into a DuPont connector. The DuPont connector was then guided through a small cutout in the main cylinder of the body and glued in place. This was done to provide an easy way of programming the Nano after everything is mounted to the ceiling. The other end of the USB cable was put into a mirrored DuPont connector. If I want to flash new code on the Nano, I can just plug in the cable into the connector from the outside, flash the program and remove the cable. The cylinder has 2 more slots for DuPont connectors, so I can add more in the future. The control unit has several components that are connected to each other. The first overview will be centered around the Raspberry Pi, and 2 other components will be covered afterwards. The Raspberry Pi is connected to the display with a standard ribbon cable. Both the display and Raspberry Pi are connected to a 5 volt power supply by a USB splitter cable. The Raspberry Pi also uses its GPIO pins to connect to the logic level converter on a PCB. This PCB gets 3.3 volts from pin 17 and ground from pin 9. For data transfer, the Raspberry Pi is connected to the logic level converter with pin 11 or GPIO 17 to L4, pin 13 or GPIO 27 to L3, and pin 15 or GPIO 22 to L2. The next PCB contains 2 bidirectional logic level converter and pins for the Raspberry Pi and other devices respectively. This setup was created because I wanted to implement communication between a Raspberry Pi and other microcontrollers. The problem with this is that the Raspberry Pi's GPIO operates on 3.3 volts, whereas the microcontroller normally operates on 5 volts. Connecting both logic levels directly can damage the Raspberry Pi over time, which I did not want to risk. Anyway, the wiring of the PCB is straightforward, with pins for the Raspberry Pi on the left and pins for the microcontroller on the right. The ground of both systems is connected, and the power lines for 3.3 volts and 5 volts have separate pins. The 3.3 volt line is connected to the Raspberry Pi, and the 5 volt line to a separate 5 volt PSU. The 5 volt rail has some additional pins, which will be explained in a bit. The last component of the control unit is another PCB with a small step-up converter. This was done because I have another device on my ceiling that requires power, and I had some issues with the power supply via 5 volts. The step-up converter takes in 5 volts from a separate power supply and gives out around 9 volts. The distribution box is straightforward with its wiring, as you can see in the wiring diagram. It contains a PCB with several power and data lines. This is meant, as the name implies, as a point where multiple other devices can be connected to the power and data system. For example, I will use this box to provide power to a so-called 433 MHz gateway, as I want to do experiments with sending sensor data from outside, not via Wi-Fi, but via radio. All three components are connected with a single cable to carry power and data lines. These lines were referred to earlier in the PCBs. What the name Simon actually stands for will be explained later in its own section. This cable is a flat Ethernet cable and contains 8 lines in total. Half of these lines are for delivering power, and the other half carries data. The method of connecting to the cable is using DuPont plugs. The plugs for all 8 lines are shown here, with the color pairs of a solid color and a striped color above each other. The solid color always indicates a positive line. This means for power lines the high potential, and for data the primary data line. The brown wires carry the signal for the microcontroller inside GLaDOS. Because I did some mistakes during the installation of the Ethernet cable, I forgot to wire a common ground. This resulted in adjusting the communication protocol, because I now need one line to act as a common ground and can only use the other line for communication. This was actually fixed during making this video, because I had to get GLaDOS down from the ceiling anyways, and then just added the common ground. The green lines are power lines for the distribution box. The blue wires are data lines for the distribution box. They work the same as the data lines to GLaDOS. The orange lines are again power lines, this time for the before mentioned device mounted onto the ceiling. After explaining the mechanical components and the electrical wiring, it is now time to show the real assembly. The body is assembled exactly like in the Instructable, so I will not go over it in detail. In addition, a small PCB is created for the relay transistor. The PWM board, LED in the head, and the relay transistor are connected to the nano. The cables for data communication are guided through a small hole of the mounting mechanism before mounting the body. The body itself is mounted by holding the body in place so that the screw holes of the mounting bracket and the cylinder line up. There, the body is then fixated by 3 screws. Mounting the body proved to be quite tricky, and I might redesign some of its parts for easier mounting, for example a kind of locking mechanism. The body must be held in place until the screws are at least partly screwed in, because otherwise the weight of the body might lead to parts falling down and or breaking. For reaching the screws from the underside, a special tool using Lego pieces was designed. With this, a Lego axis can be mounted in a drill, and on the other end, a 3D printed gear with a built-in adapter for a screw bit is located. Between the drill axis and the bit adapter gear, several normal Lego gears are used. This acts as a sort of vertical extension of the drill and makes mounting much easier. The other way is to use a small socket wrench, but this takes a lot of time because the movement is very limited due to the connector beams of the outer ring. The control unit assembly is straightforward. The Raspberry Pi and the display are mounted on the Smarty Pi case and are connected to each other. The PCB for the logic level converter is created according to the earlier shown wiring diagram, and the PCB for the step-out converter is created by loosely centering the converter on the PCB. The exact dimension don't matter in this case. Both PCBs are then mounted on the PCB holder, which is afterwards mounted on the VESA mount of the Smarty Pi case. Lastly, all required cables between the devices are connected. The distribution box assembly is quickly done by soldering the terminals onto a PCB and then connecting them to each other. The PCB is then mounted in its case. The wire for connecting all components with each other is first cut to length by approximating the required length on the control unit, then guiding it along the desired path. The cable is then cut when reaching the body. Then another small piece of the cable is cut. This cable wraps around the cylinder of the body and depends on where the connector box is located. After that, another piece of cable is guided along the desired path on the ceiling until it reaches the distribution box. In my case, I need to cut this cable again in the middle, because I used the same cable as a power line for another device, which is also mounted on the ceiling. With all these steps, the mechanical and electrical assembly is done and the complete setup is ready for usage in programs. Next up, I want to explain how the body itself is controlled via the microcontroller inside it. The program can currently control the ring LEDs, the eye LED, each of the servers individually, and has an interface for data transmission to and from the Raspberry Pi. If you are interested in the source code, you can find all programs on my GitHub linked in the description below. The current version of the program only executes commands and does not send any data back to the Raspberry Pi. Controlling the individual components is done by sending different commands to the microcontroller, with the first number or index representing the device that should be controlled, and the second number or state representing the new state. The eye LED is controlled with the index 1, the LEDs with index 2, and the servos with index 3. All these commands can contain two states, 0 for off and 1 for on. This means that the servos can be turned on or off to save power and to minimize noise because they whine when left on. Another command with index 4 can control each servo individually. This command is structured by sending a command with the index first, and after that the new angles for the head, neck, body and center servos in this order. The communication protocol was written by myself, and I will come back later to how it works after explaining the rest of the microcontroller program and the Raspberry Pi program. When starting the program, the PWM board is initialized first. Then the I/O pins for the eye and LEDs are initialized and set to 0. After that, a method for homing the servos is called. This is currently a method that just moves all servos to a known position and then storing this position internally. Lastly, a method for initializing the communication protocol is called, but this will be explained later. The loop function is very simple, with it just calling the input handler method and then starting over. The input handler method processes the received values from the communication protocol. First, a decision is made by looking at the total length and the first digit of the received data. The first digit is referred to as control mode. If it equals to 3 digits, the received command is a toggle command, where a component just needs to be turned on or off. If the length of the received data is greater than 12 and less than 18, and the control mode equals to 4, the servos need to be moved to new positions. In the first case, another decision is made based on the control mode after extracting the second digit, which is referred to as control state. If the control mode equals to 1, the eye needs to be toggled. The control state is passed onto a method, where the control state is used as a Boolean state of the corresponding I/O pin. If the control mode equals to 2, the LED needs to be toggled. The control state is used just like with the eye and is passed onto a method, where it is used for toggling the corresponding I/O pin. If the control mode equals to 3, the servos need to be toggled. This means that the servos should be powered on or off, not changing their positions. If the positions of the servo should be changed, the new positions are extracted from the received data and passed onto a method called setServos. This method changes all servo positions to the new received positions with linear interpolation. This was implemented to avoid quick movements of the servos, which lead to the body swinging around for a bit due to the big resulting force acting onto it. First, the servos are turned on, and after that, a while loop is entered. This loop continues until all servos have reached their destination positions. For each servo, first it is checked whether the destination position is already reached. If not, it is checked whether the current position is less or greater than the destination position. If it is less, the current position angle is incremented by a value of 1. If it is greater, the current position angle is reduced by a value of 1. The new current position is then passed onto the object of the PWM board to move the servo motors. After all servos, it is checked whether all destinations are reached. If so, the flag for the while loop is set and the method halts. After the check, a delay of 10 milliseconds is implemented to slow down the overall movement. The last line in the setServos method turns the servos off to save power and reduce potential noise by the servos. The program of the Raspberry Pi is more complex than the microcontroller program. Please note that this program is far from perfect and rather consists of multiple code pieces glued together. This is also why the program is called GLaDOS_temporary, because it is not a good solution. Regardless, I will make it available on my GitHub so you can cringe at my spaghetti code. Because of the state of the program, I will not go too much into detail as I did with the microcontroller program, but explain it a bit more abstractly. Anyway, the program can do the following things: voice recognition, sound output, self-written communication to microcontroller, which will be covered in the next chapter, and handling a number of different commands. The voice recognition is done by using a library called CMU Sphinx 4. This library is available for free on their website and is a Java port of a voice recognition library. It comes with pre-trained models for the recognition so that I can just use it for my purposes without any training. Using this library is a bit tricky at first, but once I knew how to do it, it worked pretty well. This library uses a so-called JSGF grammar file to specify which words should be recognized. This means that this library cannot recognize any word with good precision, but needs a specified vocabulary. Another thing is that this library doesn't know the word GLaDOS, so I had to get creative with coming up for a solution to this problem. When I ran the voice recognition without the grammar file, I noticed that when I say GLaDOS, the voice recognition actually recognizes the word lettuce. I implemented a short list of commands that I want to go over. The first commands, hey and OK GLaDOS, are to activate the rest of the commands. I implemented this keyword functionality so that the voice recognition does not misinterpret what I say into a defined command. The next two commands, hello and hi GLaDOS, are just there for fun, where GLaDOS will greet back when picking up these commands. After that, the list contains more commands that are only usable if hey or OK GLaDOS were used prior. The first command, turn off, will exit the program of GLaDOS, where GLaDOS will ask for permission before execution. This asking for permission uses the next two commands, yes and no. I have also implemented a command to exit the activated voice recognition. This was done because sometimes the voice recognition still interprets the activation commands into anything I speak. The next two commands are for controlling the Raspberry Pi, where the command shutdown shuts down the Pi and the command reboot restarts the Pi. Controlling features like the LEDs or the eye of GLaDOS can be done with their own commands, with two commands to turn them on or off respectively. Next up, I implemented a sleep mode, because I sometimes want GLaDOS to not be active. This mode disables the voice recognition and all servos for a set time and activates everything afterwards. The next command, reset communication, was implemented because the system has still some issues with the communication between the microcontroller and the Raspberry Pi. This command resets the software module for the communication. The last two commands, pause recognition and shut up, are similar to the sleep mode, except it only turns off the voice recognition, but still moves the servos periodically. Starting the main of the program creates an object of the input processor class. This class contains all the software components and logic to handle all the different voice commands. This is done by creating a thread and then looping in it until the exit condition is met. Another component of the program is the sound class. This class is to convert strings of the English language and numbers into sound output with a speaker. The sound output is realized by splitting an input string into its individual words. This is done with a recursive method that adds all words in the correct order to an array. This method also checks if a number is present and will call another method to convert it into words. The array with the words will then be looped over, where each word will be played individually. This means that the program needs a sound file for each word. Luckily, I found a zip with most of the dialog lines of GLaDOS from Portal somewhere online. I mapped these files first with their content and then began to search for the required words in them. If a required word was not present, I either found another solution or stitched a word together from the samples. And yes, I know that 15.ai is a great alternative solution for this type of problem, but when I wrote the program, I didn't know of the website. I will probably use it later in the project, but more on that later. The last component of the program is the Simon class. This class uses the Raspberry Pi's GPIO pins to transmit data between the Pi and the microcontroller inside of the body of GLaDOS. Currently it is set up to work in one direction, where the Pi sends and the microcontroller receives. The method sendSimonData takes a string as an input and sends it to the receiver. The method readSimonData does the inverse, meaning that it reads from the sender and gives a string as an output. How this protocol actually works will be explained in the next chapter. This should cover the most important things about the Raspberry Pi program and all of its features. I originally wrote a program similar to this, but with more features. They were unfortunately very crude and not implemented very well, so I decided to create a version of it that can properly run without creating too many errors and enables me the basic usage of the whole system. Next up is the self-written communication protocol called Simon that was mentioned multiple times earlier. First up, I want to explain why I did this. I wanted to learn more about how fundamental wired data communication between electronic devices works. For this, I took other protocols for inspiration and then built upon that. Was this necessary for this project? Absolutely not. But where's the fun in using a library of someone else when I can implement it myself and learn a lot along the process? Note that this attitude was not applied to the voice recognition, because I didn't have as much of a background in general voice recognition, or rather machine learning etc., to implement it myself. Though I will probably try it myself at some point, but more on that later. With the why out of the way, next I want to explain what Simon actually means. Simon is an acronym for Scalable, Independent Microcontroller Operating Network. Basically, this means that this is a communication protocol that should be used by any microcontroller with multiple devices on the bus. The whole protocol is very similar to I2C, but with a few features I added afterwards. The protocol normally uses two wires, one for a clock signal and the other one for data. This is only possible when both devices already have a common ground. If this is not the case, I also created a variation of the protocol, where one of the two wires is used as a common ground and the other wire for data. The operating voltage is determined by the device with the highest operating voltage. This voltage is generally 5 volts or 3.3 volts. In the case of GLaDOS, the microcontroller uses 5 volts and the Raspberry Pi 3.3 volts, meaning that the operating voltage is 5 volts and logic level converter are required for the Raspberry Pi. The data transmission happens with defined lengths of pulses, each standing for other states. This version is also currently used in GLaDOS due to a wiring mistake that was mentioned earlier. The protocol is theoretically able to handle many devices on one bus, but this still needs to be tested. Each device gets a hard-coded number for identification. The communication starts with the sender by sending an enable signal so that every other device listens and don't start a transmission on their own. The sender then gives the receiver number on the bus and waits for an answer. If the receiver answers with a simple response, the sender begins with sending the data over the bus. The receiver then sends the received data back to the sender, where it is checked for being a duplicate. If the sent data equals the received data, the sender responds with an acknowledge signal. If not, the sender sends the data again. This is currently done indefinitely and will probably be reworked with a timeout. The implementation with two wires without a common ground means that the overall transmission speed is reduced compared to the version with a common ground. The reason is that in the non-common ground, the different types of signals are realized by signals of different length. The shortest signals are the pause and 0 signals with a factor of 1. The other signals are 1 with factor 2, enable with factor 3, and disable with factor 4. Factor means that a minimum signal length can be changed with a constant in the code, and all signals will be scaled on this minimum signal length. Currently, the minimum signal length used in the overall setup is 1 millisecond. Tests showed that going lower than this causes some issues with the data transmission because signals are not recognized correctly anymore. Later on, I added the usage of Fletcher 16 checksums. This was done to enable the receiver to compare a calculated checksum with a received checksum. The advantage of this is that the receiver doesn't send the whole signal back, saving time in the communication process. The disadvantage is that this method is not safe for single-bit errors, but more on that later. The implemented version for the temporary GLaDOS setup is a simplified version of the overall protocol, because I spent a lot of time trying to find out where some issues come from. The simplified version worked as a temporary solution and needs to be reworked in the future. This version of the protocol only sends one command to the receiver, which contains the receiver number, the command, and the checksums. The sender then waits for an answer from the receiver, and if it is 8 times 1, the transmission was successful. If not, the command is sent again until a counter reaches a threshold. If this happens, the protocol is resetted and the transmission restarts. If the transmission is successful, an end signal is sent so that the receiver stops listening for the commands. I wrote 3 different versions of the program for the body, each containing another version of the Simon protocol. The temporary setup uses the code named MK0. If you are interested in more details of the code, you can find all code in my GitHub linked in the video description. This chapter is meant as an overview for several tests I did to get to the current state of the temporary program. The test programs will not be available in the GitHub, as they are crude tests and most of the tested stuff can be found online as tutorials or examples. Stack Overflow also provides a lot of great code that one can glue together. The first component that was tested was the voice recognition. For this, I created a simple program for learning how to use the voice recognition library. Here, I tested different setups of the grammar file, for example a more modular design, where I collect numbers in a smaller group and put the small group into the main group. Once these tests were finished, I wrote the module for voice recognition in the temporary program. After that, I played around with sound output. Here, I first tested how sound output works generally in Java, and after I got sounds to play, I came up with the concept of splitting a sentence into its words, and then playing each word as a separate sound file. Here, I also tested around with changing the voice of the played sound files, which can actually be done by storing another set of the same words for the new voice and then changing the path before the sound file. As I use a display on the Raspberry Pi, I want to control when it should be on or off. For this, I researched a bit online and eventually found out how to control the displayed state. In Java, this is done with a runtime object. This runtime executes a given command in form of a string. I use these 2 commands to turn the display on or off, where the deactivate command means to activate the screensaver, which enables after the given delay of 0 seconds. The reset command means to deactivate the screensaver. Next up are tests for the body program. First, I determined the movement ranges of all servos by sending a new target positions to the microcontroller and then noting them down. Originally, it was planned to just send the angle directly to the microcontroller, but I later shifted to using arrays with predetermined values and then sending their index. This reduces the amount of sent data by quite a lot, since each sent character results in 8 bits being sent. During the tests for the server ranges, I noticed that some servers had trouble with keeping their positions, which resulted in them making quite some noise. Having this permanently in the background all day long was not an option for me, so I looked into available functions of the PWM board library and found a command to turn the PWM on or off. This results in the servos losing their original position, but they also stop making noise. The servos will go back to their supposed positions when turning the PWM output back on. The second test involved control of the small and large LEDs and the relay via the GPIO of the microcontroller. This is done relatively simple, because it just consists of connecting the components and then toggling a digital pin on the microcontroller program. This was still required to have a baseline for digital I/O control of the complete body program. The next big testing phase was Simon. I tested a lot during the development, from simple I/O control over using a logic analyzer to verify the send signals to connecting to microcontroller and sending commands via terminal. After quite some time, I got the communication between my temporary microcontroller and the microcontroller in the body of GLaDOS working, where I could send commands via the terminal and the body executing them. The last step was to port everything from C++ over to Java and repeating the tests, this time between the body microcontroller and the Raspberry Pi. The last test phase was for completing the temporary program of the Raspberry Pi and the body program. Here, I went through all dialog options and verified their behavior. After some debugging, I finally got it to work to a state where it is usable. I noticed during the first long-term tests that the communication between the Raspberry Pi and the body microcontroller breaks down at some point, and the Raspberry Pi gets caught in an endless cycle of sending data to the microcontroller, each time without any response from the microcontroller. After going over a lot of information about several topics regarding the whole setup of GLaDOS, I want to sum up everything and then give you an idea on how long it took me and how much it costs to build such a setup yourself. Here are the main takeaways from the covered chapters. I found a model of GLaDOS online with building instructions, which I printed, painted, and assembled. The mechanical assembly, the electrical components, and connections were explained in detail. The developed program for the microcontroller in the body of GLaDOS was shown and the basic functionality was explained. The same was done for the program for the Raspberry Pi, where I covered the individual components. A quick overview of the tests done was given. Now to the most interesting values for some people: how much time and money did I spend on this project? It turns out that the whole project up to this point costed me €538.19. This value does not include unused, redundant or broken equipment that was also bought for this project. But it does include some prints and equipment for future upgrades or things that I'm actually working on right now and or wasn't mentioned here. This means that the given value is the minimum price for all required physical parts, including some tools. The 3D printed parts alone make up €37.08, the rest goes to mechanical and electrical components. Time-wise, I spent around 513 hours in total on this project, covering the entire time span from starting the project until the date of this video. It took around 248 hours to get the body mounted onto the ceiling, with 140 hours of that for the prints alone. The development of the body program itself wasn't that time consuming, but the development of Simon sure was, with 106 hours of development and testing. The Java program took around 110 hours in total to develop and test. The rest of the time went into aspects that were not covered in this video, for example the R&D on the microphone direction detection, for which I uploaded a video not so long ago. Most of this took so long because I learned a lot during the development and I did not have any time pressure because it is a hobby and not a job. The temporary program was not really used since the time around making the previous video last year, and the body program was replaced by a simple program to toggle the relay when flipping the light switch and thus giving power to the body and therefore the microcontroller. The reason for this is simply that I did not want to use a temporary setup as a long-term solution, especially with the communication breaking down after some time. I intend to use the system as it was shown when the time is right and the programs are updated to a proper state. After covering all things done, I also want to give you an insight to what I plan to do next with this project. The first thing, with probably the highest priority, is a complete makeover of the temporary program. Here, I plan to develop a proper UML first to create a proper object-oriented Java program and not some glued together spaghetti like it is currently. For this, I need to develop a scalable way of doing different tasks multi-threaded. I have some ideas for that, but the actual development will show if it will work. When I have the UML completed, I want to restructure the current voice recognition. The plan here is that I want to rewrite the general class and try to implement a modular grammar. Similar to the voice recognition, I also want to restructure the sound output. For this, I also want to rewrite the general class and remove some hard-coded things to make it more modular and professional. When the old programs are restructured, I plan to also restructure the Simon protocol. Here, I want to eliminate the current problems during transmission and switch GLaDOS from single-wire communication to two-wire communication. This should make the communication more reliable and faster. In addition, I want to rewrite the protocol to not use strings for the data to transmit, but byte arrays. This should also eliminate problems with failing communication. In combination with the rework of Simon, I also want to rework the program of the microcontroller inside GLaDOS. This includes implementing the new version of Simon and some adjustments to how the servers are controlled. Some viewers suggested using different kinds of interpolations or other methods to smooth out the movements, and I want to experiment a bit for this. With a cleanup of the current setup, the next thing would be to implement a device in my home network that collects data from multiple sensors in my home. With this, I can request sensor data on demand for several applications like automatic light control or displaying the sensor data history. At some point I want to exchange the current Raspberry Pi 3B Plus to a Raspberry Pi 4, simply to have more processing power. In combination to this, I want to create a sort of GUI for the display to maybe control the lights via a software switch or to display sensor data. The next planned upgrade is the usage of the microphone direction detection, for which I actually already uploaded the video. The goal here is to enable GLaDOS to locate the speaker with multiple microphones and automatically move to that position. This depends on the R&D done separately and if the created setup is even usable at all. I also want to create a desktop application for my PC to enable communication between GLaDOS and my PC. One use case for this would be to control the tasks of the software BOINC that is currently running on my PC. BOINC is a platform for lots of scientific projects, which you can give some processing power and the projects will use it for scientific research, be it astronomy, particle simulation or medical research. I want to be able to control which project should do work packages via GLaDOS. Next up, I want to implement notifications. This means that if something happens, for example I get an email or a device is offline or malfunctioning, GLaDOS notifies me via the speaker. At some point, I also want to implement my 3D printer into GLaDOS so that I can get printer information via GLaDOS. For making it easier for me in the future, I plan to implement a system for the program of GLaDOS to update itself via a command. This saves me some time with manually copying files and executing them. When I have implemented enough additional things, I plan to create a so-called action programmer. This will be a graphical interface to program actions, meaning combination of several functionalities like turn the lights on, activate speaker, and move body. These would otherwise be implemented via a file where I would write the action numbers into, and a GUI would help greatly with adjusting or creating new actions. When I have implemented the interfaces for data collection, I would like to do some data mining and/or machine learning with GLaDOS. How far I want to go with this is not defined, as I will just begin to learn in this kind of field of computer science. Speaking of machine learning, I plan to do tests of implementing an alternative voice recognition to the currently used one. For this, I want to use a TensorFlow model and play around with it. If I get something useful out of it, I will implement it as a new voice recognition. I always wanted to do something with bots at some point, and I decided to give a Discord and Telegram bot a try. Both bots could then be used to remote control the entire system from anywhere. As the last software upgrade, I want to implement the usage of RFID. This could be used to trigger certain actions when an RFID tag is read. And as the last planned thing that I'm already working on while creating this video is to convert the used speaker of GLaDOS. As to what it should be converted to, the end of this video might give a hint. After showing you what I plan to do in the future with this project, I want to give some last words regarding some comments on the previous GLaDOS video. I noticed that a lot of people ask me to build a setup for them or to start producing and selling them. I want to address this especially here, because I don't want to answer each single comment anymore. Monetization was and will never be a goal of this project. This is meant as a hobby activity and not a job. I also don't own the rights to the 3D models of GLaDOS, and the original creator of the Instructable also said that he wouldn't sell them, which just adds to my point. I explained everything you need to know and made every essential program publicly available, so if you want to invest the time and money, feel free to build one yourself. I do not want to start building them for other people, because it would take away the little time that I have to actually work on my projects, basically stopping my own projects for several months per GLaDOS. Also, the price for work hours would be pretty much dwarf the material costs, not to mention that the setup isn't in a state where I would want to sell it to other people, because the programs are a mess and very limited in what they do. Honestly speaking, this video always felt like a big wall in front of GLaDOS. I definitely always planned to first create a video where I explain the whole setup and then work on it again, but this kind of video seemed as such a big task to me that I always delayed it and did something else. In the beginning of June this year, I finally forced myself to start working on it, and finally, it is done. I will try to cover new things I did on GLaDOS in the form of new, smaller videos, but keep in mind that these will take a while as I want to work on other projects of mine too. Anyway, I hope you found this video interesting and that I answered all or at least most of your questions regarding the setup. When I will work on this project in the future, I will try to do it in smaller packages that I can also put into smaller videos. This will force me to document my progress better and makes it easier for you to follow my progress. Lastly, I want to encourage you to leave feedback about this video, be it in the general structure or other things, as it will help me to improve my future content. I want to thank you for watching this video and wish you all the best.